Noswaith dda, a croeso cynnes iawn I chi gyd. Good evening and a very, very warm welcome to you all. I'm absolutely delighted to welcome you to the university, to this inaugural lecture by Professor Katrien van Landeghem. Now, these inaugural public lectures are a really important part of the university's outreach. They enable us to engage with our community, with our staff, students, local residents, stakeholders. But they also serve as a platform to celebrate the accomplishments of our professors. And, I think across the series, we see such a range of outstanding work from all across the university, which really, really speaks to the breadth and the quality of the research that this university undertakes. So this evening, I'm absolutely delighted to introduce Professor Katrien van Landeghem, who works in marine geology and geophysics, and who primarily studies the seabed to better understand our glacial past and to better plan for offshore wind farms in the future. Now, of course, Katrien is one of many scientists at Bangor University who are working towards supporting the marine renewable energy sector. And tonight's lecture is titled Sound Waves for Science and Society. And it connects the methodology of marine geologists who use sound waves to study the seabed with the broader concepts that we're used to of sound waves. The sound waves I'm making right now, speaking to you. By sharing experiences and dismantling barriers in this field, in this lecture, Katrien will explore how this connection can foster greater collaboration and progress in science and society. Ladies and gentlemen, please join me in welcoming Katrien to our lecture. I'm really, really looking forward to it. Diolch, thank you.
Thank you very much, Professor Burke, for that introduction. Can everyone hear me okay at the back as well? That's great, because in terms of sound waves, mine are at the limit, because I'm at the very back end of a flu, but I will try my best making this hour. So I would like to speak to you about sound waves for science and society, and the things I will show you, maps and figures and all kinds, probably too much, but it's not all my work, of course not. It's actually with the contributions by so many others, and I'm very, very grateful for those. So let me start with that. So, first I will share with you, and I hope to actually make you as excited as I am about the seabed. It's a personal obsession of mine, and I hope after this you have some of that, or you go away with some of that as well. It's of course covered by the ocean, so I'm going to talk about how you use sound waves to discover some of the seabed's properties and how that reveals the history of the environment, but also the seabed now, what function does it have, and how can we harvest that most responsibly. Then I'm going to talk about how the seabed reveals some of the history around North Wales as well, its glacial history, ice stream dynamics, and then we'll talk about what the seabed means for us today, how it can host wind farms indeed in our efforts for accelerated energy transition. And then at the end, and this is quite important to me, is how we use sound waves like we are indeed today, like speaking to each other about barriers, about widening participation in environmental sciences and geosciences, because we can have separate events, but it'd be good if it was embedded in all events, so we can actually just speak about every opportunity that we have. Okay. With sound waves, you say? Yes, we can use sound waves for the better of science and society. That's all I'll say about that. But so, the seabed is indeed covered by lots of water. Now, you can't really dive towards the seabed to make large-scale maps. You would need to indeed use something like a multi-beam echo sounder. And that is typically mounted at the hull of a vessel, and that would then emit a whole fan of sound waves. And what it does then, it will, in every direction, measure the time it takes for that sound wave to go to the seabed and back. And so therefore it can calculate what that distance is. And from that you get a topographic map of the seabed. We call that a bathymetric map. And so I'll show you quite a few in this presentation. So that's the bathymetric map I'll be talking about. We can then study the morphology of that bathymetry and indeed the landscapes that have been formed on the seabed. Very much like the time it takes for that seabed to come, for that sound wave, to come back, you also have a certain intensity that will come back. So if it meets a muddy sediment, the sound will kind of attenuate a little bit and go into the muddy sediments, and not a lot will come back. But if it bounces off a gravelly bed or bedrock, then of course lots of it will come back. So we call that the backscatter intensity. And so once again, that's a clue about what the seabed is like, not just the morphology, but in this case, what the composition is, like what the sediments would be like. Is it muddy or sandy or gravelly? And those things I'm very keen on knowing. Okay. If you then want to know what's beneath the seabed, you can yet again use sound waves by shouting just a little bit louder, and you can make a profile with a sub-bottom profiler, and you can have a look at what the landscapes might have been in the past, because it kind of shows the seabed from the past. Okay, and that brings us to the seabed revealing its history, because if we're interested in the landscapes from the past, then maybe indeed we're talking about the glacial history. And around here, around North Wales, around the UK, we have had indeed ice flowing over the seabed and leaving bed forms behind. Glacial bed forms like drumlins and ribbon moraines, and I'll show some later. And so what we've been doing, we've been reconstructing how that ice has advanced and how that ice has retreated over time. Do I have a little pointer? Yes, I do. So 26,000 years ago, we had a massive British and Irish ice sheet all the way to the southern edge of the Celtic Sea, right? And then a few thousand years later, it already zipped back, and I'll show all this in a bit more detail later, but you can see that then it retreated. And this is our glacial history. And around North Wales, here we are in the eastern Irish Sea to the north of North Wales, that would have been ice-free about 20,000 years ago. And so this reconstruction is important for many reasons, and I will touch on that later in this presentation. Now, as that ice disappeared, you can see that, of course, the sea comes in. So this is the Irish Sea, and so as the ice has retreated, the water can come back in. And indeed, the seabed will also give us a history of the oceanographic and the sedimentological properties of that bed. And so a history of currents flowing over the seabed and also leaving bed forms behind, but this time a different type of bed forms, sedimentary bed forms like a dune or a sand wave, as you can see here schematically in this diagram. So you have sand heaping up, you know, the little ripples that you see at the beach, but then much bigger. Yes, so they give us an idea about what those currents might have been in the past. And why do I say in the past? Because about 20 years ago, 5 years ago, I discovered this very, very large sediment wave in the middle of the Irish Sea. And this is not a vertical exaggeration. It is trochoidal in shape, so it's kind of symmetrical, and it gets steeper near the crest. And it's 35 meters high. That's a sediment wave, you know, one of those exaggerated ripples that you have on the beach. And I tried to fit it underneath the Menai Bridge, and it doesn't. So that clears about 33 meters underneath the Menai Bridge, and this is 35 meters. So imagine all that sand, yeah? That didn't just form in the last couple of weeks. So this indeed gives us a history of the currents of the Irish Sea. And that brings me to talking about seabed mobility and what that means in general and how that contributes to many areas really, including mineral exploration, the sustainability of the aggregate extraction, but also coastal erosion and defense. And the three things I will focus on today, as I already kind of mentioned, would be the reconstruction of ice dynamics. At the top, you see offshore engineering for wind farm purposes, for instance, and cabling and things like that. And what actually binds a lot of that is habitat mapping and modeling, because the habitat is what the seabed supports. And so I'd like to therefore start with that and say, right, This seabed, from a geologist's perspective, this is actually the logo of the geology department that I studied in Belgium, and I adjusted it a little bit to make it a little more feminine. But this is, from a geologist's perspective, what a seabed habitat looks like, and I hope the biology colleagues from my department don't mind too much having this so geocentric, but I'm starting off by saying, okay, mud, sand, gravel, and a rocky reef, for instance, what type of habitats do they support? What kind of species do they support? And then we're talking about fauna. So certain epifauna, that means the kind of animals that live on the bed, will typically, not all, but some of them will typically really prefer a certain sediment type. Yeah? And there's, of course, loads of other things that will impact why an animal wants to live somewhere, depth and temperature, of course, being some of them, but there is also this real affinity with the sediment type, okay? And the infauna are the animals that live inside the bed, and of course, they will also typically prefer a certain bed type. Now, all these habitat functions are linked, and they can act as facilitators in the wider ecosystem. What do these lovely animals do? They can oxygenate the sediments, they can improve the water quality, think of your mussels, they do nutrient cycling, and they are, of course, food for predators themselves. And if there's lots of them, they can provide shelter for other animals even, yeah? So they become their own habitat. So that is quite a kind of geocentric view of different physical habitats supporting different communities and the functions that they have in a wider ecosystem, a healthy marine ecosystem. And to really labour the point, because it is an important one, I have another slide on that. So how can the benthos then change the ecosystem functioning, and why, again, that sediment composition matters? So the fauna you've just seen, right, in the previous slide. So this is the infauna and the epifauna. Don't forget the cobble reefs and all that. But this is something I did not know until rather recently, is that the fish actually not just prefer sediments just to be comfortably lying on, but also that they have, herring, for instance, they deposit their eggs on coarser substrates, but they will recruit on a diverse substrate. Sand eels, of course, as the name would suggest, they really like pure sand. As soon as there's any mud or gravel involved, they will just move. And this is important for seabirds. And it's that link that I hadn't really made until recently. The seabirds dive to the bed, not all of them, some, and find their prey at the bed. So if those sand eels were to have moved, of course the seabirds are going to feel that. Yeah, they need to get their prey, they need to do that efficiently by having abundant prey, but also exploitable, so in a behavior that they know. Yeah, and that will then attract the seabirds to use that particular habitat. So, in short, changes in the benthic habitat has an impact on the ecosystem. And a lot of these are geological processes influencing this change. And so, will it change? Or how would it change? And over what kind of time scale? Well, this is a slide I nicked from Chris, I'm sorry. But small perturbations impact, and they can impact over large extents. So this is the Scroby Sands offshore wind farm. This is off Norfolk, and what you see here is turbines here, and this is a seabed bathymetry map, and you have these individual turbines, and you can see that there's some scour around it, but you can also see that per wind turbine location, you've actually got a seabed mobility kicked into motion. Yeah, so you have sediment waves, remember those bet forms I've shown you before, that actually in the wake of this monopile exist, and they don't outside. So they then all link. And so what happens is you have a different regime, different seabed sediment regime, a different seabed morphological regime. So that really does matter. What else matters, and this is then revealing the history and the function of a bed, is when you have an ice sheet going over a bed, it leaves also bed forms behind, as I said before, and it all depends on how that ice is going, and I'll talk about that later. But the thing is, the type of glacial bed forms and the glacial till that is left behind by the ice causes lots of lateral variability. Not like a river, because that kind of selects and sorts things out. And ice doesn't discriminate. Ice stream, doesn't discriminate. It takes anything from the tiniest of clay particles to a boulder the size of a house, and it'll take it in its path and it'll deposit it whenever, wherever. So those deposits are annoyingly variable and you can't really predict. You have to go and observe it, because an engineer, of course, would really like to know whether you're going to have to drill through an enormous boulder or through some clay sediments. Yeah. So this becomes quite important, not just to see what the history is like of this area, but also about how we're going to use this seabed going forward. But first, before we talk about how we use the seabed going forward, let's talk about those bed forms a bit more that are left behind by a glacier and what that can tell us about the environment. So this now brings me to the second part, sound waves to understand ice stream dynamics. And I would like to show you a data set. I love it because it's just in our backyard. So here we have Bangor, yes, I can't sit still, and then just a few kilometers to the north of that, a big data set collected, in fact, to plan a wind farm, but the plug was pulled on that. There is none there now. But because of this, we now know what the seabed looks like. And pardon this rainbow color scheme, it's not very good at all, but you can see, I hope, some of these bed forms there. You see it's all a bit rippled. And I'll show you a detail of it later. But first of all, this profile, is this profile here at the bottom. That's a sub-bottom profile. And you have all these bed forms here on the seabed, but we can see from this profile, they also exist underneath the seabed. And that's why it's important that we shout a bit louder with different equipment and have a look where the glacial landscapes might be buried as well. And they are often buried, so we need to actually use that technique to do so. So we find subglacial bed forms buried underneath the seabed. But, and this requires some imagination, but geologists have plenty of it, you have the top of the bedrock here. I don't know if you can see the contrast in red. So, yeah, you really can't see that, I think. But believe me, we do really think that's the top of the bedrock, and it goes up underneath that bed form. That's a minor detail, you might think, but it isn't. That means that the ice went all the way down to the bedrock and, in fact, molded some of that drumlin or whatever it is, maybe part of a megascale glacial lineation, but it got that subglacial bed form made in part from the bedrock. Yeah. So that says something about the erosive power of that ice stream at the time. Okay? Right. Let's also zoom in to this part, because that is really the intricate part, and some of you in the room I think have already seen this. I keep presenting this because this is one of the most pristinely preserved glacial landscapes I've ever seen, and it's just here off North Wales. It's beautiful. So this is a bit of a zoomed in area of drumlins, and you find glacial bed forms, of course, also on Anglesey and elsewhere, but these are on the seabed, and it's really unusual to have them so well preserved. So this would be one drumlin. You can see the scale here. It's a couple of 100 meters in length, and they're often teardrop shaped, and the kind of tail end would indicate the ice stream direction. So we can already use that to actually say, oof, actually we now know what direction the ice stream went. And then you have these more longer, thinner bed forms over the top of them. It didn't quite eradicate the drumlins. You can see they overprint a little bit here. They're flutes. And the flutes would be the same as a drumlin, but really thin and long. And that would indicate a thinner ice sheet, even so. But then, I hope you can see this, you have all these pits and drag marks. See all the pits in there? They're left by an iceberg keel mark. So what we have here is, first of all, ice streaming, then an ice sheet or an ice stream, I should say, retreating with intense carving in front of it. And of course, you wouldn't have that kind of carving and that kind of iceberg pits successively going along if it wasn't in a water body. So boom, a clue again. From just seabed morphology, we can now say, aha, this retreat was accompanied with a water body in front of it, so that means sea level would have already caught up, which is important for us to know because the style of deglaciation and retreat might well be influenced by that sea level rise and the warmth of that water body, etc., etc. So from small clues, by really looking at the seabed morphology, you get so much information. Let's labor that even a bit more. So Here again, I'm focusing on a northern area of the same data set. So once again, seabed bathymetry, topographic map of the seabed. And what we see here are those fluted drumlins that I just shown you. We also have these MSGLs. We call them mega-scale glacial lineations. They're a bit broken up, but I hope you can see that they once were large bed forms like this. And then behind it are rib moraines, and rib moraines have formed from a frozen till sheet, so that tells us something about the state of the ice. Then you have eskers, which are like upside-down riverbeds, and then all these iceberg pits, yeah? And then push moraines are the ones from in front of the ice. A little bit too much information, probably, and I regret it, but what we can do, though, and this is, I just want you to realize the potential of using sound waves to then look at the seabed and what that can tell us actually about ice sheet dynamics from, 22,000 years ago. And that's exactly it. So first of all, we look at ice advance. We know now, because it went right down to the bedrock, that must have been very erosive. We also see deep tunnel values. I've spared you from those, but the megascale glacial lineations you see, and of course it did go down to that bedrock. Now, as it goes down to the bedrock, it gets a bit stickier for the ice. And that becomes important later on, because suddenly we see a different direction of ice flow when we look at the drumlins and the rib moraines. And the rib moraines would also tell us that there was basal freezing. So why was that then? And also there was an ice flow realignment, and now we see more topographic variation, because I hope we appreciate these megascale glacial lineations indicate that there was ice streaming right over the top of Anglesey. It didn't go around Anglesey, it just bulldozed over the top. This is to go around Anglesey. Yeah, so topography related. And then from the flutes, only a very small realignment, slightly different, but really largely the same. Faster ice, thinner ice, and defined again by topographic variations. We see ice drainage because we see the eskers, and we of course see some intense calving. So it must have been an intense retreat, real quick, and then up to the terrestrial area. So I've made the following conclusions from just seafloor morphology. First, we had an erosive ice streaming period, and that actually, because it reached the bedrock, got to a sticky point, that allowed some freezing to happen. So in the end, it determined all that later ice retreat. I think that's a lot of conclusions from just some morphology. But of course, that can't be all of it. And I need people like Margot for being in the room and her expertise, because we need to date some of this retreat. So what Margot would do is she would go and look for the glacial till. And the till, that's what sits underneath the ice. And you can see the shear strength here is indeed quite high in comparison to the rest of the sediments, because it's been compacted by the ice. Okay, when ice retreats, of course, that then sits in that water body. Sediments and animals come to the seafloor. If you grab the first animal and date it, you've got yourself a date for ice retreat. That's what Margot's done. True? So all these cores have been investigated very, very carefully. Dates were taken, and so there is an ice retreat now dated. So 25,600 years ago, ice was all the way to the shelf edge. No one would believe it, actually. There is still some doubt about this, but we have proof, we have evidence, you know. So ice went all the way from pretty much Scotland. Some of Welsh ice came in and flew all the way to, scoured all the way down there. Then it zipped back quite quickly, yeah, to 25,000 years ago. Then it took its time to go to the central Irish Sea basin, and then rather quickly deglaciation of the eastern Irish Sea here to the north of North Wales. So why is it important to look at the timing of retreat? Because those retreat rates will tell us something about the mechanisms behind ice dynamics. Is it influenced or driven by external climate drivers? Is it all about air temperature, or is it all about water temperature? Or are there other factors involved? For instance, internal ice dynamics, like overextension. Clearly, it was a bit ambitious, and it overextended. And it went, I can't maintain this. So there are internal kind of physical things that have nothing to do with the climate in a way. Then there's also the topographical controls, and there is the subglacial character. And it's important that we can see what's been reacting to what kind of parameter, because of course we still have ice today, don't we? in our polar regions. So if we better understand how these ice sheets and these glaciers will retreat in response to what type of parameter, we have a better handle on predicting what might happen when and where and why. Yeah? And that's good for the modelers, of course, because then they have better accuracy in predicting sea level rise. Yeah? So we went out there, and of course, me with my sound waves, I was able to, again, map the bathymetry in the fjords in which some of this ice was pouring into. And because of a very brave captain, they went too close to the ice, and they captured some of the ice front. Accidentally, they weren't meant to go so close. And in fact, when that goes and the calving happens, you have to get out of there. Yeah? They had to do that. I wasn't there at the time. But this is now giving us a clue of the shape of this ice front. And so, with a bit of luck, we'll hear soon, we'll have funding to go back and actually direct an echo sounder right at this glacier front and actually purposely collect that data, not accidentally collect that data. So that's really exciting, and Kate is the person at the forefront of this, and she'll be lucky enough to go back to Antarctica as well. But this is, of course, when you're already in the Western Antarctic Peninsula. Unfortunately, you have to get yourself through the Drake Passage to get there, and that is no mean feat. Okay, right. So the glaciers in the polar regions, we need to understand them better, but we still have to understand the glaciers from our own past here better, not just academically, because we want to reconstruct it, but also because the engineers need to know. Yeah? And this is something that Hannah and Shagun are doing at the moment. They're having a look at these different glacial bed forms and what the different geoengineering properties are. Because remember, I showed you that core and the shear strength, and I said, look at this diamicton, it's got higher shear strength. Well, that is, of course, true, but is there any difference between the different glacial bed forms? So what Hannah's done, for instance, is have a look at normally consolidated clay, so no ice was on top of that, and overly consolidated clays, ice were on top of that. And again, you do see, quite luckily so, otherwise it would have been an awkward thesis to write, the shear strengths are indeed very high. What we did not appreciate is the differences between all these different bed forms in these numbers, because this is the end moraine crest that a core went through, and therefore we know what the shear strengths are. And I'm sure the engineers would not know that this glacial moraine would actually be as strong as a very strong rock, right? So the glacial till could be so strong because of compaction, it behaves like a rock. That's the kind of knowledge that we need to pass on to engineers so they come with the right gear when they're installing wind farms. It's quite as simple as that. Yeah? So it's really impactful science. Sand waves, because of not just the ice going over the seabed, but also the currents, have a similar, there is similar worry to the engineers. They form, of course, a huge variation in topography to negotiate, but if they move, then they can uncover your cables, they can uncover your pipelines, they can cause all kind of havoc. So we need to understand better, and Chris does a lot of this as well, and Murren is working on this. We need to know better how they move, but also how that's related to that glacial history, leaving a certain sediment behind. And one example here is what I found years ago. This one bed form, again, such a trochoidal bed form. This is the kind of seabed bathymetry map of it, and this is the backscatter map of it. So you can see it's a bit lighter over the top, isn't it, than around it. Again, loads of imagination needed in geology. We have loads of it. I hope you see it. But then we took another profile, so another type of echo sander, and again, with a little imagination, you can see that there's a fine grain sediment veneer over the top of what looks a lot coarser. Can we be sure? Not really. So we put a core down and we looked at the sediments, and it was 80% gravel, and gravel of a good 2 to 3 centimeters, and that's unusual. Gravel waves the size of this, they don't form in currents of today. They are not strong enough. And indeed, 15,000 years ago, between 10 and 15,000 years ago, the currents would have been much stronger. There would have been a narrower Irish Sea because the ice was still, the ice had retreated, but the sea level was still rising. And so this is very likely a feature of the past. So if you want to know as an engineer, is this going to move or not? And what properties does this have? Again, you need to know about the history of the area. Yeah? Okay, so then. Number 3, how can we indeed help accelerate? Oh, I was already on number 3, wasn't I, for a while ago? Sorry. How will this bentos now change in the future? Because I was talking about the history and how the history impacts, and what engineers need to know about the history. But then you put your wind farm down, and how can things change after that? Well, this is what we study now, and this is from a wind farm just here offshore North Wales. A wind turbine there with the scar protection around it, which is kind of that donut shape. And in the wake, you can see all rippled bed or sand waves in the wake, whilst just next to it, there isn't any. This is very likely very clean sand, and this is that glacial till that we know is exposed. Yeah, that hosts different habitats, right? That hosts different animals. Same wind farm and another turbine, and it's the opposite that's happened. You already had sand waves everywhere, because that was just the regime. But in the wake of it, the currents kind of accelerated in that wake and just wiped them away. So we have regime changes here, habitat changes here, and we need to know about them. The offshore renewable energy needs to know about them, because they need to go and predict them and tell us how they're going to mitigate against that. And so we have quite a big question here. Off North Wales, in particular, this Eastern Irish Sea, you see from this colourful map with a legend that you don't have to worry about, just look at the colours. You can see these are all the habitats assemblages in the whole of the UK waters. You can find all of them in this patch. In other words, all the habitat assemblages that exist around the UK exist offshore North Wales. Yeah? Then you have all these polygons. What are they? The existing wind farms and the ones that they are planning to put in place with a cross. Yeah? So here, the seabed hosts infrastructure and most of the UK's benthic habitats. So we need to find the answer to the following. What is the impact of these wind farms, but also put in context with climate change, of course, on the seabed sediment mobility, on the habitat distribution, the biodiversity and the ecosystem services, and on the interaction between habitat, prey, and seabird foraging. And that is exactly what we're doing in a project called EcoWind Accelerate. We're going to have a look at number one, how does climate in general, but also sea levels, of course, and wind farms change the bed stress by 2050 and 2100. We have a look at how the different seabeds, because they're often a mixture, will therefore host different habitats. We'll see who wins and who loses. The sand eels might not like it, other animals might do. And then we'll have a look how that impacts the seabirds. Yes? Do they gain energy or do they not? That is the nuts and bolts of that big project. We use our own vessel, the Prince Maddock from Bangor University, and we're going to co-locate everything there is to know about the habitat, the seabed habitat, about the prey that use that habitat, and about the seabird behavior. And so the next few slides are about that. And I'll begin with Chris's work. He uses data from the field, again acoustics, that you put on frames, and from the ship as well, because you want to co-locate the changes in the flow and the changes to the bed. And you want to do that where the wind farms exist, and we have good working relationships with the wind farm developers. They allow us to pretty much bump into their wind farms. It's great. Then we go into a lab, and we mimic what the situation is offshore, and we make sure we get that process right as well. By using acoustics and laser, what's the flow, what's the bed, how does that change? Then, if all goes well, you do some numerical modeling, and you see if that fits what you've done in the lab, and if that fits what you've done in the field. Yeah? And then you tweak until it does fit. But that numerical model, and the way you've tweaked it, is going to be crucial to then apply that at a larger scale for a larger wind farm and even neighbouring wind farms. So we need to get the physics right before we can go to a larger scale. And that is by linking these processes from the field scale to the lab scale. And so far, we've already seen some things that collaborate or corroborate, I should say, that the effect on the bed form seems to be up till about 17 times the turbine diameter, which is pretty large. And then we can compare that to what happens to, for instance, with a storm. And this is what Julia Ruland in NOC helps us do. And this is still from Chris's work. So here you have that same environment. So we have the seabed bathymetry, a wind turbine, a bed frame here, a bed frame there, and there. So this is 25 meters away, and that is 200 meters away. You can see the amount of stresses on the bed from currents that have amplified on the bed. And that's here, and you can see, near the wind turbine, that near the wind turbine is in blue. That's actually up to 3.5 times. A bit further away, in fact, a lot further away, it's still up to 2 times. So that's quite the impact. 200 meters away from a turbine, you have twice the amount of stress on the bed compared to the background stress. But then Julie does a bit of modelling and she says, right, this is what one storm does. And in this particular area of North Wales, you would actually have the stresses amplified 5 times. So this allows us to say to the policymakers, look, don't just look at the local impact of a wind farm. How does that relate to impacts from one passing storm? Now, this one passing storm, that's only a couple of days potentially, but it could have long-lasting effects on the bed. So we are going to be in that space and look at these counterfactuals. Wind farm, climate. What about the climate? Yeah. So that's what we're doing at the moment. Then I have a team of habitat modelers and mappers, and Lisa in NOC is now getting Bridget on board, who's our own PhD student, and they're looking at this species habitat association. What's the difference outside and inside a wind farm? So once again, these are the types of sediments. What are the kind of animals that end up living there? No pictures, please, because this is very much work in progress. So this association is something that we're building up from thousands and thousands of images of the seafloor, including from the monopile itself, the monopile base, the seabed just in the wake of the monopile, and from the scar protection as well. There's this rock armoring that we get. So that's something that we do to complete the picture. And then, this is what I have most admiration for, actually. Olivia Hicks and James at Ocean Sciences, they look at seabird behavior. And the stars need to align for this. You need to follow those chicks. You need to tag them. You need to have a look at what comes out on either end. And all needs to just align. And you have to co-locate all that data, because the end result is that you can assign diving seabird behavior and have a look what the different areas are, how they are most profitable for the seabirds in terms of their prey. So they map, for instance, from tagging the birds, when they dive. So these are all the dives, individual dives. This is how they move. And this is like what the energy expenditure would be as they do so. So this proxy for energy expenditure is really important, because we need to know if they need to go further out, like one bird did here, how much energy will they have lost by doing that? So if we take away some habitats here and they have to go and dive there for their food, what does that mean for their survival rates? Yeah? And that really is the nuts and bolts of it. We're having a look at this fine-scale relationship between seabirds and the seabed. And so, of course, we need to do that by also looking at the fish. And so this is what we do. Fish and diving birds, we plot all that on top of each other. And I can hear some of you think, well, some of you might think, is it nearly 7 o'clock? But some will think, this slide has no acoustics on it. It does now, because how do we get the fish? We actually have information of that fish from an echo sounder that will also show you where the fish schools are and where they are in relation to seabed bathymetry. Yeah? And then you go and trawl them and have a look at what kind of fish these are, and then you compare them to the video images that we collect from having little cameras on these seabirds. Honestly, I'm so glad I'm with sediments in the lab, but it does make for some fantastic science. So this is all in progress, all in motion, and this is going to be really exciting to do. And the reason why it works so well, I've been told, is that the seabirds are a very well-behaved colony here in North Wales. And also because we have so many different habitats around here, so we can test the hypothesis so well. And luck would have it, it's in our backyard again. Okay, other impacts with sound waves. So now sound waves on every slide. You can check they really were. At the end it was close, but we just about managed. But we need to make sure that impacts from our vocal cords and the sound waves that we make that way are indeed beneficial to science and society. When I was in my undergraduate in Ghent in Belgium, I had an opportunity to go through a training program. It's training through research. And I could go on a big research vessel with all the best scientists of the whole of Europe, really. And it really did open my network. in the end, in fact, I used one of the people who I met, as a referee for my PhD application, and in fact, that person also became my external examiner for my Viva. So it opened up my network, and it's really important because these types of training isn't just about science and education. It is, of course, very important, especially because it's so practical on a vessel, but it also gives you access to a large network. So what this person, Ben Fisher, I'm helping him, but he does all the legwork, does. He's only a PhD student, but he's, with some NERC funds, is setting up a portal, and it's called Find the Science Berth. And this is to say, look, on all these really large vessels out there, not so much on our Prismatic, that's usually quite full, but on really large vessels, there's often berths available. And there are so many students out there who don't have that kind of typical network opportunity in the marine world. So how about we give everyone a chance to come on board and just experience the science, experience the network, and benefit forever, like people like me have done. So great credit to him. And one of my dreams really is that we would use the Prince Madoc also for science and widening participation. If we do have space on it, that we have people to come on board and learn and have that network forever. Then I went to Antarctica. I keep boasting about it because it was quite the experience for me. It was the experience for me as well because I hadn't even spent a day in the office yet after a year of maternity leave, and I got on a boat for 5 weeks. So for me, that was quite something. So it was a fantastic environment to be in, as you can see from the pictures I took myself. But I did struggle a little bit because I was leaving 2 small children behind. So what I did, I took pictures of these 2 cuddly toys and I sent them to my kids. It was more for myself than for them. But the fact that I was this time not the only woman on board, which I have been for years, right? And that's now changing, and it has changed for a while. And I could just share some of that experience with people who were thinking about making their own family or having their own family soon. And I have actually since heard that my experience and me sharing that experience with them have made an impact on that decision for them to start a family and to be confident that you can have a family and a caring, duty, and as well as having a nice academic career. So that is important. So widening participation matters. And it's better now for women, but we are doing still very poorly for ethnic minority groups. And this is some data that I analyzed, from a paper in 2001. So I kind of got the data myself, and I had a little look at what it meant. If you look at the percentage of the population between 18 and 24-year-olds, you can say, well, those are usually the ones going for undergraduate. Then you can see the biggest drop-off, the biggest leak in the pipeline is either not applying or having a low acceptance rate, because this is at undergraduate level, But then the retention is okay, So what is the reason behind that? So it would look at, let's look at the acceptance rate, and this is where I took some UCAS undergraduate data, dashboard data, and I used the ethnic diversity data in that. And although it's getting better, have a look at black women. Why is it that they have started off from this low and they're catching up? Boy, is there work to do. And so those are the problems that we have, because actually when I was looking at the data for NERC, 29% of the awardees for PhD students didn't even have any data assigned to them. So of course then we can't be doing any good studies then, can we? But there is a problem in NERC. If you look at, say, the PhD studentships, there's 12% in the whole of the UK. UKRI is about 10%, but the Natural Environment Research Council, only 5%. So why is that? And that's all for environmental sciences. And then we were wondering, what about the geosciences? We can't strip out that data so easily. They're not, the granularity doesn't exist on these dashboards, so we had to do our own work and have a look what the barriers might be. And so a couple of years ago, we sent out a big questionnaire, and this was actually led by Steve Rogers, and about 600 people did a reply, so it was good enough. And we just wanted to know, okay, what is geosciences for you? Why did or did you not apply? And what do you think about, employability and things like that? And what were your barriers and how might we solve this? And so it was quite crushing to hear that everyone found it boring. And so that was the main comment. It's boring and it's old-fashioned, and you're just knocking on rocks. I said, what? So it's perceived as mostly white masculine. Good point. That it really assumes that you're physically able to go into the field. Good point. And actually that the field work is perceived to be very expensive. That's not always the case, but the perception counts. Yeah. So what do we need to do about this? It's uncomfortable to read this about your own kind of science topic, but let's lean into the discomfort, shall we? We need to do that, because otherwise we're not going to cause any change. So some of the recommendations: let's connect geology to societal needs and concerns. I think we're starting to do that, aren't we? And we need to also change the story there, because, of course, the societal needs and the concerns used to be oil and gas, and everyone still thinks that's what geosciences are. But they're not at all. I think my entire talk today was geosciences, nothing to do with oil and gas. Yeah. So the discipline is not diverse, so we need to really tackle that, and we do that by looking at the discipline itself and how we can apply it. Yeah. So the storytelling within that is important. But of course, we can only have a good story and a relevant narrative if you indeed talk about sustainability, take that seriously in the energy transition projects and the activities, and if you make good emphasis of how geosciences can help there. And I hope, and that's going to be my last thing, that the work that we do here at Bangor University, and that I'm also involved with my healthy obsession with the seabed, that these essentially geological processes help us understand wider ecosystem processes as well, and that we directly inform and try to improve the planning for and the sustainable management of offshore wind farms, for instance, for a better energy transition. And I think I'll probably leave it there.
Thank you, Katrien. That was absolutely fascinating. Really, really great talk. Thank you. We've got some time for questions, so can I ask you to raise your hands? We've got microphones. If you could wait till the microphone comes so that everybody can hear the question, that would be really helpful. So have we got any questions? There we go.
Oh dear.
Just a simple one, Katrien. You've got a picture there of your LiDAR radar doing the seabed, and in all of those pictures the sea is like a sheet of glass. What happens as the boat goes up and down? Does that affect the rate at which the sound waves travel up and down? They've got longer to throw at the crest of the wave than they would at the base.
That's a very good question. We do that to trick people, so they do indeed engage in marine sciences. But the answer there is that we have a very, very accurate positioning system on the vessel. So as the vessel goes up, it will tell in real time what its position is, and it'll actually make the correction in real time. So this is almost as expensive as the echosounder itself. So a very good, what we call, POS-MV, a positioning system, is crucial to good seabed bathymetry data. But it does that in real time. We don't have to do any of that ourselves. And in fact, they do this so well now that the positioning of the vessel is in both XY, but also in the Z direction. So your vessel becomes a bit of a tide gauge. Because, of course, as the tide goes up and down, you would also say, well, your seabed surely isn't coming shallower and deeper. So that correction is also made in real time because it tracks the motion of your vessel, but also in this way, because it does do that, of course, with the waves. Yeah.
Thank you. Any other questions?
So could you say a little bit more about taking core samples to verify your sound analysis? Some of those core samples seem to be in pretty tricky situations.
Yes, they are, especially in conditions like Richard says, but we would have to have calm conditions, and then you have many ways of coring. Either you drop a core, it's called a gravity core for that reason. You drop it and you hope for the best, and then you retreat. Or you think, do you know what, this is quite coarse sediment, we're going to have to just lower down the whole instrumentation, and then we're just going to slowly vibrate the core down and then retrieve it. There's many ways, there's other ways, but those are the two main ways that we would use in environments around us. And then you have a core tube, but all the sediments within that. You often take some kind of geophysical and geotechnical properties without disturbing the core just yet, and then you have to open it up. And then you have two halves. One half you work on, like Margot would do, and get all the animals out and get all the sediments out, and the other half you leave for archiving. And then you store them usually very cold somewhere. Yeah. Does that answer your question?
Stop at the bedrock, obviously, then.
Yes. The core liner is going to stop at the bedrock, yes. But if the industry wants to go deeper, then they would be using a head with actually diamond-shaped rotating things, so they can drill all the way down. Yeah, of course, yeah. But that's not what we would need to do, because actually our interest usually stops at the bedrock. We do focus on what we call the overburden, because but this is the archive of all those past processes. The bedrock isn't necessarily, yeah.
I'm worried this is a ridiculous question, but I'm going to ask it anyway. Do you have to be on a boat to map the seabed, or could you do it from a plane?
That's a really good question, actually, and this is one of the things that we need to use for widening participation as well. There is so much work out there to do with the data and modelling, and to be a marine scientist, you do not have to be in the field, you do not have to be on a boat, and there's so many people who work on polar ice caps and have never been to Antarctica. They don't want to go, it's too far away, they don't have to go. So it's an option. So no, you don't have to. And there are so many different jobs in this field that either require you to travel or they don't. It's up to you.
I guess that's a great answer. I guess I wasn't asking so much from the perspective of if you get seasick, but more you can cover more ground with a plane. So can some of these things be scaled up to use satellites or aircraft, or is there some kind of barrier with the surface of the ocean that prevents that from being used?
There is a big drive now for unmanned vehicles and boats, and they can do the work. Because of the problem that you have with the positioning, the data is of less quality, but actually it is good enough. And of course, you save on a lot of CO2 that way. Yeah. A lot of these autonomous underwater vehicles still need a babysitting vessel. So you don't save a huge amount that way, but you can send a few of them out and be more effective that way. And in fact, this is a big drive now from the research councils and the governments to make our science environmentally more friendly and more effective, and try to upscale things like that. The technology is just about keeping up with that. But it's an exciting time. I think this is where we're planning to go. Yeah, that's a good question.
Thanks, Katrien. I've never enjoyed a talk about mud as much, if I'm honest.
Another question down here. Thank you.
You've talked a bit about changing the amplitude of the sound waves, the loudness, but you haven't said anything about the frequencies that you use.
Yes, because if I go on a tangent, we'll be here until 10 o'clock. But you're very correct. So the frequency is usually defined by the range that you want to achieve. So if you wanted to, say, map the bed that was 10 kilometers underneath you in the middle of the Atlantic, you have to use a lower frequency, because that means the sound waves will go like this, and they will go for a longer range. They don't interact with the particles so much. A higher frequency wave will do this, but it'll attenuate faster. But that's ideal for shallower environments. And then you'll also have a better map as well, a higher resolution map. So it very much is defined by your goal. So a different system for a different environment. Yeah.
Just behind you.
Hello. I believe the fishing is not allowed in the farms, around the farms. Is that right?
By and large, it's not necessarily the case, and I think in the future, when the wind turbines are going to be a lot larger, it's about 7 times the span of one of these, and they're becoming 300 meters, 400 meters. So these turbines will be a good kilometer to 2 kilometers apart. Whilst now, the older ones are only 500 meters apart. So, of course, that becomes an exclusion zone just for safety reasons. But we might have to rethink that in the future when these are further apart. But often it's seen as a compensation measure, to make sure that some of the damage that was caused from the construction of the wind farm is uncompensated by the fact that it becomes a bit of a marine protected area inside of the wind farm. Now, of course, some of those rules are policy from the fisheries themselves. You know that there's a sand eel ban now, but that has implications then for the wind farm industry, because they thought the sand eel ban was going to be one of their crucial mitigation pathways. And now that's taken away from them because it actually comes from a fisheries policy point of view. So they're now in trouble.
It does make a difference to your results, would it?
Here we have the mature wind farms from Rail Flats and Gwentymore, and the fish that we actually look at is not inside the wind farm. This is from across all the different habitats outside the wind farm, because we want to look at the fine-scale relationship between the habitats, the fish, and the seabirds. And of course, the seabirds aren't going to often be inside that wind farm. They're going to stay away because of the blades. So we do that research outside the wind farms. Yeah. Thus to establish that relationship.
So it does make your results within the wind farm would be different than normal. It's not a normal.
And that's why, we don't actually look at the fish inside the wind farms. What we do know is that well outside the wind farms, the sediments can change. And it's where they might change that the seabirds might find a different habitat. So we don't quite focus so much on the fish and the seabirds inside the wind farms, because that's going to be a bit tricky. This is where direct collision, that becomes more of an issue. Yeah.
Right. Thank you very much.
Hiya. It might relate kind of to that question, but as you've said, in Wales, we've got like a really high abundance or diversity of the sediments on the seabed. Have you found yet an ideal place that would have least impact on like the fisheries and everything that you're researching in Wales? Like, is there an area that you should be avoiding with all these different sediment sizes in, or should you be looking at areas with the same?
We haven't just yet, because you might think you've been at it for a year and a half, Katrien. Come back in another year and a half, and I might tell you. It takes a lot of effort finding that fine-scale relationship. It also takes a lot of effort getting the models right. And then we're going to model what's happening in 50 and 100. We haven't quite done that yet either, because the environmental modeling went in first. So it does take a long time. And, academics just take their sweet time with everything. But yeah, no, we are looking at that. But of course, the plans are going ahead. So we need to almost race a little bit against that time and make sure that we can influence some of these wind farms, construction decisions with our preliminary results in mind. And this is a little bit different from what we used to do as academics. We would want to have the research and then through peer review, and that takes another year and things like that. But now we have to be a bit comfortable and pushing things out before we have them fully peer reviewed, and roll a little bit, but soon is the answer to that question.
Any other questions? One at the back, Paul.
You showed right at the beginning a very interesting, very large feature. How did that form, and are there likely to be similar ones elsewhere within the locality?
The sand wave that didn't fit underneath the Manor Bridge? Yes. We thought it was an enigma at the time, and we've now found with lots more seabed mapping, they're everywhere. And because they're so coarse, you actually have scour marks around them. They're really, really interesting. The trachoidal shape is always the same, and that's because they have acted almost as a barrier for the currents on either side. So they really are fantastic to look at. Now, the 35 metre, that's the record. That's the highest I've found so far. I haven't found anyone else who found the higher one. And this is 100 metres of water depth. So it's a third of the water column is this massive feature. So, of course, the oceanographic processes will also be influenced by that. We haven't even touched on any of those processes and having a look at, there is a lot more to do with those bed forms. But I can see you're equally now mesmerized by the seabed. I think I've passed on some of my obsessions. Great. Oh, yes, true. Yeah.
Thank you. But perhaps I could just finish with one question, which is linked to that a little bit. But what areas of the ocean around the world are the most mapped? And are there some that are not really touched at all yet?
Yeah, so the most mapped might actually be the Irish seabed. So when I started my PhD, you might hear from my twang, I'm from Belgium, but I did my PhD in Ireland, and that was the start of the Irish National Seabed Survey. So the government ring-fenced money for that seabed survey to continue and for their entire EEZ economic zone to be mapped. And that, in the meantime, has happened, which is a great advantage to have for their use of the seabed. It's only because of legislative reasons that they haven't gone as far in their wind farm developments as the UK has. So the UK is lagging behind on that front. And I would actually hope as well that the Welsh government, with all the plans in their waters, would also do something about seabed mapping and make that ring-fenced budget ready available. There's a fantastic vessel that is equipped with the best echo sounders to do such a job, and it tells you immediately what the seabed composition is, what the dynamics might well be. This is what Chris works on as well, using morphology to actually predict better what the dynamics might be. And then immediately, whoever wants to apply for a lease has so much more information about what might be the big challenges for their project. And so, I would make a plea for the UK to do more of a coherent effort in seabed mapping, because it gives you a huge advantage in terms of the energy transition as well. Yeah.
Thank you. Can we all give Katrien another big round of applause for such a great job? Thank you.